I'm going to talk. So thank you very much for the invitation. I realize climate is something that a lot of people think about. Not too many people know stuff about. As physicists, you guys are in a unique position to really understand the problem in a way that most people don't. And let me begin with some news. Not new news, but news nonetheless. This is an article from the New York Times, October 28th, 1956. Warmer climate on Earth may be due to more carbon dioxide in the air. And there's 2 points I want to make about this. Number one, nothing I'm going to show you is new. Or very little of it is new. There may be a little new stuff at the end. But this is all stuff that's at least years old. Most of it's decades old, and some of it's hundreds of years old. So this is a problem we've been working on for a long time. In addition, let me show you a quote from this. Dr. Gilbert Plass, he says, to him, the carbon dioxide theory stands up, though it may take another century of observations and measurements of temperature to confirm it. 1956. Now, for those of you who don't know who Gil Plass was, he was the head of this department from 1968 to 1977. So this department actually has a very profound connection to climate change. Gil Plass is one of my heroes. Unfortunately, he died the year before I came down here, so I never met him. But his stuff is very influential. He was really the first person to work out radiative transfer in the atmosphere. I'll be talking a lot about that today. And I think if he were here and he saw this talk, nothing in it would surprise him. It would be like, yeah, that's what I thought. He'd be impressed at how much data we have. He'd be impressed with the computers we can use that he didn't have. But he wouldn't be surprised by anything. All right, so where to begin? Let me start off with my conclusions. So if you fall asleep after this, you'll still have come out with the points I want to make, except for one conclusion at the end I'll add. And the first one is the Earth is warming. We're in the midst of a very long-term warming, goes back 100 years. And it's warmed about 0.8 of a degree Celsius. It doesn't sound like a lot, but that is a lot, and I'll explain why. Most of the warming of the last 50 years is extremely likely to be due to human activity. And I'll talk more about that later. I mean, humans are now in the driver's seat of climate. We've got our foot on the gas, but unfortunately we don't have our hands on the wheel. Likely warming of the 21st century will be a few degrees Celsius. And again, that doesn't sound like a lot. I'll explain why that is a lot later. And the impacts of this, I mean, nobody knows how much warming we're going to get, really, whether it's 2, 3, 4 degrees. Nobody knows how bad that's going to be. But we can say that the worst case scenarios are really dire. So those are the things to remember. And then there's one more conclusion which I'll add on at the end. So the first one, I'm going to go through these kind of quickly, some of these. I'll spend most of the time on the physics of why we think carbon dioxide warms the Earth, since I think that's the stuff you guys will think is most interesting. So is the Earth warming? I'll just show you some data. So this is probably the most well-known kind of data. This comes from surface thermometers. So you have year on this axis. This is temperature anomaly. That means it's just a departure from a mean. So usually the mean is 1961 to 1990. That's probably what they're using here. They kind of shift it every once in a while. And basically what they do, for about the last 120 years, there have been enough thermometers across the surface of the planet that you can get a general average temperature. And so this is just the average of thermometers across the planet. And you don't have to be a rocket scientist to see that there's a trend going up, especially since the 70s. But a longer-term trend than that. There's some interesting things. There's sort of a drop here. There's interesting year-to-year variability. But the long-term trend is really clear. And if we put on 2015, not over yet, but we're 9 months into it. 2015 is probably going to be a few hundredths of a degree above 2014. And 2014 was the hottest year in the record. So it's hot. It's a hot year. Now, if you look at a map of where it's hot, it's the east coast of the U.S. is one of the few places that's not blisteringly hot this year. So we've actually had a pretty pleasant summer as far as College Station goes, a reasonable year. But just about everywhere else on the planet, it's been incredibly hot. Now, in any single data set, there are lots of things that can go wrong. All right, so there are lots of ways you can think, well, there could be errors in this data. There could be urban heat island effect. There could be errors in the calibration. There could be all sorts of problems. How do you know what your coverage is? Coverage can change. So you don't ever rely on a single data set, and we don't rely on a single data set for the conclusion the Earth is warming. And so we look at lots of data. So, for example, satellites. So satellites can also measure temperature. Since about the late 1970s, we've been flying satellites. They measure in the microwave, so they can see through clouds, and you can get a temperature of the bottom layer, about the bottom 8 kilometers of the atmosphere. And and both of those show warming, and they show about the same amount of warming. So that's a good validation of the surface thermometer record. In addition, if you look at ice on the planet is disappearing. So various forms of ice. There's sea ice in the Arctic. There's glaciers. There's the big ice sheets. They're all melting. Now, there's always nits in the record. So if you look at the Antarctic ice, it doesn't look like it's quite behaving the same way. But on the other hand, that's also consistent with the fact that you expect the ice to disappear fastest in the places where the temperatures are warming fastest. So it's warming fastest in the Arctic, and that's where the ice is disappearing fastest. So in general, we see ice melting. In addition, most of the heat trapped by greenhouse gases goes into the ocean. The ocean, if you look at the heat capacity of the climate system, it's mostly in the ocean. The oceans are 4 kilometers deep over 70% of the planet. The heat capacity of that is just enormous. And so most of it, the heat content goes in there. And again, if you measure the heat content of the ocean, not the surface goes into the surface thermometer record, but the temperature of the bulk of the ocean, that's also going up. And finally, we see sea level going up. And sea level is connected to the ice and the ocean heat content. When the ice melts, when grounded ice melts, you expect that to raise sea level. When the ocean heats up, water expands, you expect that to raise sea level. So in some sense, this is a sanity check on these, and sure enough, they fit together. So it's like puzzle pieces that fit together. It's not independent data, but data that fit together in a web. And so the first thing to realize is these are all independent measurements. Any one of these data sets could be wrong, but the odds that they're all wrong and all wrong in the same direction is really small because there's no single error that you can think of that would affect all of them. So for example, surface thermometers, you could say, well, urban heat island could be a problem. The fact is if a city grows up around a thermometer, it'll measure warmer temperatures because cities tend to be warmer. But that's not going to affect the satellites. And so the fact that they agree really suggests that there's not a problem in the surface thermometer records. And again, as I said before, the ice is independent from these. The ocean heat content's independent. They're all independent measurements. And again, they fit together. So E.O. Wilson uses the word consilience to explain how data fit together to be stronger than their independent pieces. And so because of this, the IPCC refers to the warming of the climate system as unequivocal, meaning essentially beyond doubt. And so I think that's right. It's very hard to argue that the climate system isn't warming. And I'm not going to talk about the argument that global warming stopped in 1998 or something. If you want to know about that, ask me later. But just because I want to cover other things, I can't talk about everything. Suffice to say, I don't think there's any merit to that argument. All right, so let's talk about carbon dioxide. So we know the climate system is warming, and so then you say, well, why is it warming? What's causing it to warm? And so we can look at this like physicists and say, okay, well, let's start with the first law of thermodynamics. And this actually goes all the way back to Fourier's original analysis in the 1820s. And so energy in for the planet has to equal energy out for a stable climate. So that's the fundamental energy balance law that rules climate. And so energy in comes from the sun, and I won't go into this. S is the solar constant, 1,360 watts per square meter at the Earth's orbit. A is how reflective the planet is, what they call the albedo. It's about 0.3 for the Earth, which means 30% of the incoming photons are reflected back to space. And you can work it out, and so the average incoming radiation is about 240 watts per square meter. So then the Earth has to radiate that in order for the climate to be stable, because if it's not, then energy is accumulating, the climate will be warming up. So we can look at energy out as just sigma t to the fourth. Just treat the Earth as a black body. And we know that has to be about 240 watts per square meter also. Again, it's got to be, if the climate isn't changing, then those two have to basically be in balance. If they're not in balance, then the climate's going to be changing. And so what you can do is you can take this, you can say, well, what's the radiating temperature of the planet? And it's about 255 Kelvin. That means if you're in a spaceship and you have one of those infrared thermometers and you pointed it at the Earth and you said, what's the temperature of the Earth? It would read 255 because that's the radiating temperature of the planet. The Earth has to be radiating at 255 K in order for it to balance energy in from the sun. Okay, so then what does this tell us? And that's minus 18 Celsius. Okay, so let's do a quick diversion, a little more physics of convection to explain why the temperature profile in the atmosphere is what it is. We live in what's called the troposphere. It's the bottom layer of the atmosphere. It goes from the surface to 10 to 15 kilometers in altitude. Tropo is Greek for turn. This is a layer of the atmosphere that turns over rapidly, as opposed to the stratosphere, which doesn't have strong vertical motions in it. So the troposphere has big vertical motions. You see them in thunderstorms, lots of air going up fast, and then in clear skies, the air is sinking. And so it's turning over rapidly. Now, when an air parcel rises, it expands. And as it expands, it does PV work because it's got to push back on the atmosphere. And so the parcel cools off as it expands. It's sort of adiabatically ascending. It's expanding. It's pushing back. It's got to cool off. And so that leads to the temperature profile that we all are kind of familiar with. This is temperature in Kelvin. It's, 300 at the surface. This is pressure in millibars or hectopascals on the y-axis, 1,000 millibars, 1,000 hectopascals the surface. Airplanes fly at about 300, 350, and 100 is about the tropopause. That's the top of the troposphere. And you see the temperature goes down with altitude. We all kind of know that. If you're going to go hiking, you take a coat because you know it's going to be colder as you go up higher altitude. And again, the reason the temperature drops off is because the troposphere is turning over, and as air rises, it cools off. And so that defines this negative lapse rate. And this turns out to be incredibly important. The greenhouse effect is going to rely on the fact that as you go higher in the atmosphere, the temperature goes down. So we know that I did the calculation before that the Earth has to be radiating at 255 Kelvin. That's the fundamental energy constraint. If it's not radiating at 255 Kelvin, then it's not balancing the energy coming in. And so we can say, well, where is it 255 Kelvin? Well, it's 255 Kelvin at about 500 millibars, which is about 5 kilometers altitude. So if you ask, where's the radiation that's escaping to space coming from? It's actually coming from the mid-troposphere. It's not coming from the surface. Photons emitted down here get absorbed in the atmosphere. I'll talk a little bit more about that in a second. It's only photons that are on average emitted here that make it up. Now that's an average, so it depends on wavelength, but for this conceptual model, just imagine all photons emitted at this level make it escape. Photons emitted down here don't escape. Okay? All right, so this is the fundamental point. Now let's do a thought experiment. Let's instantaneously double carbon dioxide. Let's ask ourselves what's going to happen. Okay, so all the photons are escaping from this level, but then when we double carbon dioxide, the photons no longer escape from this. We increase the infrared opacity of the atmosphere. So now photons are escaping from this slightly higher level because the atmosphere is now more thicker, has a higher optical depth in the infrared because we've added carbon dioxide. Now, the important thing is, see if people are sleepy or not. So why is that? How does that affect the climate? You're emitting, does anybody know? Nobody? All right. It's important because it's colder here. It's now emitting from a colder level. So let's go back to our fundamental equations. This hasn't changed. Energy in is still 240 watts per square meter. But we're no longer emitting at 255. We're emitting from a colder level. That means that the energy out has decreased. So if you instantaneously double carbon dioxide and hold everything else the same, you decrease the amount of energy you're radiating to space. And this means that energy in exceeds energy out. And it's just a first law problem. If energy in equals energy out, you're accumulating energy, Cp dt. your delta temperature is positive. You've got to be accumulating, temperature's got to be rising in response to the fact that the climate system is accumulating energy. And so what's going to happen? Okay, so we know we're accumulating energy, and so the climate is going to start warming. And it's going to warm until this new emission level is at 255 Kelvin, because that's the fundamental constraint of the climate system. The Earth has to be radiating at 255 Kelvin in order to balance energy in. So it's going to shift the temperature profile over until it's now back with an effective radiating temperature of 255, because that's the only way the planet can establish energy balance. And so put a different way, if you ask the question, why is our climate the temperature it is, it's because that's the temperature that gives you energy balance. And if you do anything to the climate system, if you add carbon dioxide, if the sun gets brighter, if a volcano goes off, the climate's temperature will adjust until energy is balanced. And so temperature is how the climate system establishes energy balance. I think I just repeated myself like 12 times. Forgive me. All right. The net result, though, is that you've warmed the surface a little bit. If you assume a constant lapse rate, and you can ask me about that assumption later, but we're assuming the lapse rate is constant, so you end up warming the surface by adding carbon dioxide. Again, this only happens because temperature declines with height. If that weren't the case, if our atmosphere were isothermal, there wouldn't be a greenhouse effect. If our atmosphere was like the stratosphere, it increased temperature with altitude, then by adding greenhouse gases, you'd cool the climate. But this is the way it is, so adding greenhouse gases warms the climate system. Okay, so let's talk a little bit of physics. This is why you're here. And so everything I've talked to you now is what I'll call the black atmosphere model. The atmosphere absorbs all photons and it emits like a black body. But we know the atmosphere doesn't actually do that. So let's imagine, in fact we have these, that you have a spectrometer in orbit. And the spectrometer is looking down at the atmosphere and it's measuring the intensity with very high spectral resolution. Now, let's sort of ask the question, what is it going to see? All right, so let's start off with an atmosphere that has no greenhouse gases. So oxygen, nitrogen, and argon, which make up 99% of our dry atmosphere, 95% if you include water vapor. But the vast majority of our atmosphere is those three constituents. And this is basically what the spectrometer would see. This is microns on this wavelength, intensity on this wavelength. And for those of you that really care, this is a tropical clear sky atmosphere, 299 Kelvin surface temperature. And so let's put some black body curves on this. And so the blue line is the model I showed you on the previous plot, and these other lines are black bodies. And with no greenhouse gases in the atmosphere, if you had a spectrometer looking down, you would see a 299 Kelvin black body, because the atmosphere would be doing nothing. It wouldn't be absorbing or interacting with the IR photons emitted by the surface. And that's basically what it looks like. The surface is just a black body, and that's exactly what you expect, and that's essentially what the model produces. So let's start adding some constituents and seeing what happens to what the spectrometer sees. So this is ozone. So ozone has a very strong absorption at 9.6 microns, and you see there's now this big divot in the profile. And so what causes that? Well, what causes that is, remember, the satellite is looking down. It's looking down, but it can no longer see the surface at 9.6 microns because ozone is optically thick at that wavelength. So it's seeing some point in the atmosphere, say the mid-troposphere, and it's a lot colder there. So if we go back to this plot, we're seeing colder temperatures in the mid-troposphere. And in fact, you can design an instrument that measures the temperature of the mid-troposphere. In fact, you can, well, I'll talk about that in a second. And so, but basically that's what's happening. So you're seeing the satellite can't see all the way to the surface. So what it's seeing is it's seeing some layer in the atmosphere between the 280 and the 260 Kelvin black body surface. Black bodies. All right, so let's add methane. So methane has a line at about between 6 and 7 microns, somewhere around there. And so methane also absorbs, and again, at those wavelengths, again, you can't see the surface anymore. So you're seeing some atmospheric level. And we'll add water vapor. So I'll sort of flip back. So water vapor is really the big dog as far as absorbing infrared. You can see the huge impact that water vapor has. I mean, you essentially can't see the surface in any wavelength because of water vapor. There are a few wavelength ranges we call the atmospheric window around here where you can see pretty close to the surface. But you can't see the surface. All you see is water vapor at different levels of the atmosphere. And so, in fact, what I was going to say before, I'll say now, you can actually create a sounder to measure a profile of temperature in the atmosphere by judiciously picking wavelengths and saying, you know, this wavelength sees this altitude, this wavelength sees this level, you know, these wavelengths see almost the surface. You can actually measure temperature at various layers in the altitude by selecting wavelengths that go to various depths into the atmosphere. And so now let's add carbon dioxide. And I'll flip back and forth so you can see. So carbon dioxide creates what my colleague Ray Pierre Humbert calls the CO2 ditch. It's right here at 15 microns. It's a very strong absorber, and it's so optically thick that you're basically seeing into the upper. It only goes into the upper troposphere. So you're seeing 10, 12 kilometers. You can't even get close to the surface. This spike right here is actually not you seeing lower. It's so optically thick there that you're in the stratosphere where the temperature is rising again. So, how much what?
How much the water?
So this is carbon dioxide is 280. Water, I actually don't know. It's a climatological tropical profile. So it's whatever they put into the model. So this is and I should say 280 parts per million. This is mole fraction. And so it's mole fraction, it's parts per million. So it says that out of every million moles, 280 of them are carbon dioxide. This is pre-industrial. So if you went to a 1750 atmosphere, this is basically what the spectra would probably look like. Okay, so let's go to let's compare now CO2 at 280 and CO2 at 560. And remember, this is what I talked about earlier when I showed you those profiles. And so this is 280, and you really can't tell the difference. So what we're going to do is I'm just going to integrate and give you the total energy out. And so the energy out for this 280 parts per million is 294 watts per square meter. And if you remember, I said energy in from the sun is 240. This is bigger than this because this is cloud-free, and it's in the tropics. So it's hotter temperatures, and there's no clouds. So don't worry about the exact numbers. What I'm going to show you here is what is sort of the important point. So if we double carbon dioxide, we're going to push up the emission level, and E out is going to go down. That's what we're going to show you. And sure enough, it goes down by about 4 watts per square meter. And that's where I came up. If you remember earlier, I said if you double carbon dioxide, your energy out goes down from 240 to 236. This is basically where that comes from. That if you double carbon dioxide, you reduce energy out. And again, you do that by pushing the emission level up. And so the planet is going to warm, and it turns out that it's going to warm by about 1 degree. So doubling carbon dioxide, if everything else stays the same, gives you about 1 degree of warming. Now, if that were all there were to the problem, we'd be done. We could go get cake or cookies and coffee. But it turns out there's more to the problem. And this is actually the easy part. The hard part is coming up. And the problem is that not everything else stays the same. So as an example, here's the plot I showed you before. Here's the emission level before we double carbon dioxide. Here's the emission level after we double carbon dioxide. The temperature profile is warmed. But a warmer atmosphere has the property that it holds more water vapor. And water vapor is itself a greenhouse gas. That means in this atmosphere, your water vapor is going to increase, and that's going to cause more of a temperature increase because it's a greenhouse gas. So put a different way, you warm the atmosphere, you get more water vapor. That pushes the emission level even higher than the carbon dioxide by itself. And that means it has to warm up, because remember, the emission level has to be 255 Kelvin. That's the fundamental constraint. The climate will do whatever it has to do to make sure it's emitting at 255. And so this gives you additional warming of the climate system. Now, I'm not going to talk it's impossible for me not to put in some of my own research, and I'm not going to give you a lot of details about the water vapor feedback other than to say that I have worked on this for a very long time. This is 2003, 2007, 2008, 2009, also 2009. I'll skip that. So we have a lot of data on the water vapor feedback. So we have a lot of data on carbon dioxide. We have a lot of data on water. I mean, we can really take that to the bank. We know that's going to happen. You add carbon dioxide, you push the emission level up, the atmosphere is going to become more humid. That's going to push the atmosphere up some more. And I'm going to gloss over a lot of other stuff and just sort of put it all together and tell you what you get. So you double carbon dioxide, gives you about 1 degree. So water vapor by itself adds another degree to that. So water vapor doubles the direct impact of carbon dioxide. And then when you add other feedbacks, which I haven't talked about, we call the lapse rate feedback, the surface albedo feedback, cloud feedback, that gives you somewhere in the neighborhood of 1.5 to 4.5 degrees C for doubled carbon dioxide. And the middle value is about 3 degrees Celsius. So what that means is that of the warming you get when you add carbon dioxide, only 1/3 of it comes directly from carbon dioxide. 2/3 of it come from these feedbacks: water vapor, clouds, surface albedo. And in general, we are very confident in these feedbacks. Water vapor, I'm not the only person that's been publishing ad infinitum about it. Lots of people have. Lapse rate is also very well understood. Surface albedo simply relies on the fact that when you warm the temperature, you melt ice. We're pretty confident that ice melts reliably at 0 degrees Celsius. Clouds is really the big uncertainty. It's hard for us to really narrow it down, but if you take sort of a Bayesian perspective and say, I take everything I know, what's my estimate of the probability that the models are getting it about right, and it's pretty high. The models could be wrong, but we don't really have any evidence that the models are way wrong on those. And I'll just say Gil Plass in 1950s came up with a value of 3.6 for doubled carbon dioxide. So my hat's off to him. Turns out he was lucky. There were a lot of things he didn't know, but he made a bunch of errors that canceled, and so he ended up getting a number. I mean, the stuff they didn't know was amazing. No one had ever taken a picture of the Earth at that point. Nobody had any idea of what fraction of the Earth was covered with clouds. I mean, they knew so little that this is really it's a heroic calculation to do it with that little data. But again, as I said before, if Plass were sitting in the front row, he would look at all this and he'd be amazed at the data we have, but nothing would shock him. It's like, yeah, well, that's what I thought, that's what I thought, that's what I thought. Okay, so what does the future hold? Okay, so given a climate sensitivity estimate of, say, 3 degrees Celsius is in the middle with some sort of range, you can look at estimates of what atmospheric carbon dioxide is going to be. Now, we don't know what's going to happen. It depends on what kind of policies we adopt. So I put on here, you saw, we have one policy is drill, baby, drill. This is, it's known by the less interesting name of RCP 85. And that's the world where we drill we dig all the coal out, we dig out the tar sands, we burn every last drop of hydrocarbons we can find. And that's what carbon dioxide is going to look like if we do that. At the other end, we have the world I call Ed Begley Jr., which is everyone's driving a Prius and recycling their urine, I think. I don't know. But everybody is the world does a maximum effort to reduce emissions. And in this world, emissions actually peak in about 5 years, 2020, which is not going to happen. And CO2 peaks in about 2050. And actually, CO2 emissions go negative in 2080 as advanced farming techniques pull carbon out of the atmosphere. And so by the time you get out to like 2200, 2300, carbon dioxide is below what it is now. This is very unlikely. I think this is a lot more likely, unfortunately, than this. But nonetheless, these worlds span the possibility of worlds that we could experience. It's probably going to be somewhere in there. It's going to be somewhere between this ridiculously green world and this world where we burn every last drop of oil we can find. And if we ask ourselves what happens in this world, This is basically it. So this is the drill baby drill line. This is Ed Begley Jr. right here, and these are the two middle scenarios. And so to give you some context, the 0 here, for reasons that are endlessly irritating, is referenced to 1986 to 2005. So that's the average, and it's degrees above that. Whenever you hear people talk about, people have probably heard 2 degrees Celsius, that's reference to pre-industrial. So you want to add 0.8 degrees to these to get the reference to pre-industrial. So the Ed Begley Jr. is about 1 degree above the late 20th century. So it's about 1.8 degrees above pre-industrial. Drill baby drill is about 5 degrees above pre-industrial. Now you think of those and you say, that doesn't sound like a lot. I mean, what's 5 degrees Celsius? I mean, last night was 12 degrees Celsius colder than this today. Winter's going to be 50 degrees Celsius colder. What difference does 5 degrees Celsius make? And the answer to that is that your intuition of what's a big temperature change is based on these local changes that don't translate well to global changes. If you ask the question, how much colder was the Little Ice Age? So the Little Ice Age was a period in the late, around the Revolutionary War, early 19th century, and it was significantly colder then. In England, they had winter festivals on the Thames where people would walk out on the frozen ice. George Washington, the Continental Army, almost froze to death at Valley Forge. There are lakes that froze over that don't freeze over anymore. It was significantly colder back then. And if you look at the global average, that's 1 degree. It was 1 degree colder than it is now, 1 degree Celsius. And if you cool the climate 1 degree, you get a little ice age. And to get the real ice age, last glacial maximum, it's about 5 degrees. So if you cool the climate by 5 degrees Celsius, about 10 degrees Fahrenheit, you get glaciers covering much of North America. You get 3,000 feet of ice over Boston. So these small changes, these changes of a couple degrees, which don't sound like a lot, because they're based on your local perspective, when you apply them to the global average, these are huge changes. So, we have changes that are comparable to the warming we had since the last glacial maximum. And I mean, at last glacial maximum, we had a different planet. Sea level was hundreds of feet lower than it is now. Ecosystems were different. It was just a completely different place to live. And if we do this, who knows what it's going to look like. But I guarantee it's not going to look like it does now. I mean, things will be different. So finally, let's go back to Lapse and Science in Review, and I'll sort of sum up with a quote he said. In a few centuries, he warns, the amount of carbon dioxide released in the atmosphere will be so large it will have a profound effect on our climate. So I'll just say that's right. I mean, we've been working on this. He said it may take a century to prove that. And, that was 60 years ago. And, everything we have demonstrates that theory is correct. If we dump a lot of carbon dioxide in the atmosphere, we're going to warm the climate a lot, and it's going to have a big effect on the way the world works. Now, it doesn't tell you what to do about it, but that's science. All right, so I've got about 10 minutes left. I'm going to spend the last 10 minutes answering a question that I didn't sort of pose at the beginning, and that is, if the science is really this certain, then why are people arguing over it? Why is it? Why can't people just look at that? Why don't we sort of have agreement on the science? And it's really an interesting question. And I started thinking about it when I realized the following was true. I have never met a person who thinks climate change is a hoax but likes Obama. I mean, think about that. Those should be uncorrelated opinions. One is a scientific question about your evaluation of the science of climate change, and the other is a policy question about what you think about, Obamacare and his appointment of judges. Those ought to be uncorrelated, but they're not. They're very strongly correlated. And then I ran into some data. So this is not anything I've done. This is data from someone at Yale named Dan Kahan, who's a psychologist who looks at the way people cognitively make decisions. And I saw him give a talk, and I was just blown away by it. And basically, he showed some data. As a scientist, I love data. And he showed data And so we can make a really strong argument about why it is that people disagree. And basically the first thing he showed me was this plot right here. So he asked the question, how much risk do you believe global warming poses to human health, safety, or prosperity? And then he had people rank it. And then what they do is they can ask you a bunch of other questions, and they can figure out where you fall on the political spectrum. So they don't ask the person, what are you? Are you a conservative Republican? They can ask you questions and figure that out. So, this is Elizabeth Warren, I guess. This is Ted Cruz. I think I would put Obama and Hillary. They're sort of left of center there. Who knows where Donald Trump is? But the point of this is there is a very strong correlation between your views, your political views, and your views on climate change. And so I saw this, and I thought, this is the question I was asking. Why are your views on climate change and your views on Obama correlated? Because they clearly are. And so you look at data like this, and as scientists, the first thing we want to do is we want to create a hypothesis. We want to say, what could explain it? All right, so one hypothesis is what Kahan calls the public irrationality theory. This idea that people don't know enough science. If they knew more science, they would understand and everybody would agree. So you can think of, there are two different groups, egalitarian, communitarian. These are liberal Democrats, hierarchical individualists are Republicans. So this is what psychologists, this is how they sound smart, I guess. There are no psychologists here, are there? All right. And so the idea here is that this is how much science you know, and this is sort of what people think about the perceived risk of climate change. And the idea is that as you know more, you get this convergence of what you think the risk of climate change is. Now, I've drawn it here, or actually Kahan drew it here, where they're all sort of converging on high risk. But it could converge anywhere. It could converge down here. It could converge here. But nonetheless, it's going to, the idea that it's the polarization is because people don't know enough. The test is, do you see convergence as people know more? And so again, you can look at the data. And the answer is, not only did they not converge, people become more polarized the more they know about it. So if you look at here, these are the Republicans and these are the Democrats. You see this gap is bigger than it is for people that are low comprehension science. And so this really destroys the idea that it's just that you just have to explain the science to people. And when I saw this, I thought, of course, because I've been trying to explain the science of climate change for 20 years, and I guarantee I've never had anybody change their opinion. And it's not because I don't know what I'm talking about. It was something else. And not only do they not change their opinion, they get angry at me. They actually get mad when you explain. It's like, well, that's not really how it works. Here's the data. Pretty soon, they're stomping mad. And so I knew this is right. And in fact, the people who are the smartest are the people who are the best able to do that. All right, so let's have another theory. All right, so we're going to do what we call the skin cream experiment. And so what they did is they had a bunch of people answer the question. They gave them these data. So there's a skin cream. Patients who did use a skin cream, this many, the rash got better, this many, the rash got worse. People who did not use skin cream, this many, the rash got better, this many, the rash got worse. And they asked the question, did the skin cream work? And you can see, it's not very hard that, and I'm sure everyone here would get the right answer, that the skin cream does not work. If you use a skin cream, only 3/4 of the people got better. If you don't use a skin cream, over 80% of the people got better. So the skin cream does not work. But I guess let me go back and just say one thing. There are a lot of cognitive traps you can fall into if you aren't good with numbers. You could look at this. You could say, well, 223 people got better. Only 107 people didn't get better. Only 107 people got better if they didn't use it. So obviously, there are lots of ways if you're not good with math, you could fool yourself. And in fact, I just want to say that they did a bunch of tests so that it wasn't the wording of the question. They asked some versions where this column was rash got worse, others were this version where rash got better. And if you look at the data, it looks kind of like what you'd expect. This axis is how good people are at numbers. This axis is how what fraction they got right. And you see that as people get to be better at numbers, their chance of getting the right answers go way up. And these are the two different ways they ask the question. Maybe there's some differences. These people are getting the answer right about half the time, maybe a little less than half the time here. That's unfortunate. But these people who are good numbers, they're getting the answer right almost all the time. And this is what you expect. There's nothing surprising here. And in particular, if we sort people by political classification, we don't see a difference. Republicans are as likely to get this right as Democrats. And the reason is because there's no political salience to this. Nobody cares. Nobody's political identity is tied up in skin cream. So let's look at something that may be a little different. Gun control. Let's ask them exactly the same question, but instead of skin cream, it's a gun ban. Did the gun ban work? So cities that did ban handguns, cities that did not ban, decrease in crime, increase in crime. By exactly the same logic, the ban did not work. And that's because crime decreased in 75% of the cities that banned it. It decreased in over 80% of the cities that did not ban it. So you can look at it, you can work it out, you can get the right answer. And so the question is now when we give it to people, what do we see? Oh, and again, they swapped the ways to do it so there was no bias in how the question was asked. And we see something really interesting. Look down here. So if you give a liberal, a Democrat liberal, you give them data that shows that a ban works, they get the right answer. You give a Republican data that shows the ban didn't work, they get the right answer. You show them data that doesn't agree with what they want to see, they don't get the right answer. I mean, this is data. This is not anecdote, this is data. We see that these people don't get the right answer. It's not that they can't get the right answer. They get the right answer up here. They don't get the right answer because they don't want to get the right answer. People's identities, people's view of the world is tied up in these answers. And if you don't want to get the right answer, you think of some reason to not get the right answer. And people out here, they're really smart. They're really smart. They can come up with lots of reasons to not get the right answer. These people, they'll never get the right answer regardless of what they think. They're sort of hopeless. And so this is really, in some sense, profoundly discouraging. If we look at what's normal, what should we see? So this is fluoridation. Again, this is Republicans, Democrats. And you see there's no difference. There's some wingnuts, but their wingnuts are equally likely to be in either party. And most people, they don't view fluoridation as very risky. This is what you expect to see. This is medical x-rays. Again, what you expect to see. You don't expect people to be interpreting science through the lens of their policy views. If we look at climate, we see something which is pathological. That it's completely skewed by their views. And so if you say, well, why is this happening? Why does that mean? Well, individuals are being rational. They want, if you're a politician, your electability is dependent on what you say. So, Newt Gingrich, Mitt Romney, they're smart guys. They know climate change is real. They said so many times before they ran for president. But once they started running for president, they had to adopt their views normally. And in fact, if you don't adopt the right view, you'll get kicked out of the group. So if you're a barber in South Carolina and you're cutting people's hair, you don't want to talk about climate change with them, and you certainly don't want to tell them something they don't want to hear. I mean, what's the advantage for you? What's the benefit for you? They're going to think you're weird. You're going to lose customers. The rational thing to do is to adopt the views of all your group, especially when there's not a huge cost to you. The barber in South Carolina probably thinks climate change isn't really going to have a very big effect on me. I mean, he may be wrong with that, but that's his implicit belief. And in that case, he's being very rational. So people who adopt these views are doing the right thing for them. But the net result, though, is that society does not use the best available science to make its decisions. Instead, people are arguing over science. This is a classic tragedy of the commons, where people do something that's in their best interest, but it's in society's worst interest. And so if you sort of say, well, what do we do about this? I think what we need to do is convince people that that climate change and the solutions to climate change don't actually conflict with their overall worldviews. I mean, if you believe in small government, there's a addressing climate change is still probably the right thing to do, even though it might have some government intervention now. Imagine what's going to happen if there's a huge drought and food becomes short. The government's going to move in. They're going to be controlling who eats and how much you eat. After natural disaster, there's always much more government intervention. If you don't want government intervention, you don't want a lot of climate change. If you want freedom, you want the climate to be stable. And because once it starts changing, bad things are afoot. And so, and I won't go on and on about that. So I'll just sort of conclude. The Earth is warming. That's really unequivocal. Humans are now a dominant influence on climate on a centennial time scale. I mean, unless a big volcano erupts or the sun suddenly changes, we will be the dominant influence on a centennial scale. We still won't control it year to year. Things like El Niños, things like other oscillations will control it on the decadal time scale, but on longer time scales, those things average to zero, and humans will be the dominant influence. Like I said, we got our foot on the gas, but unfortunately, we don't have our hands on the wheel. We're likely to see warming during the 21st century of a few degrees, and the impacts of this are severe. I mean, these are, the other thing I'd like to point out is that human society as we know it, with million people cities and industrial agriculture, we have developed during a period where the climate has varied by a very small amount, much less than a degree. And so if the climate changes by 4 or 5 degrees, we have no idea what's going to happen. But again, the impacts of this could be really terrible. Maybe they wouldn't be. I mean, who knows? But it could be really bad. And the arguments about this arise because of pathologies in the debate, because of the way people interpret data, because of the way they think about being part of the group. And sort of the most successful thing that whoever did this in the debate, the most successful thing they ever did is they made membership in the Republican Party be determined by your views on climate. And so if you don't have the right views on climate, you become a heretic, essentially. And nobody wants to be a heretic. Politicians don't want to be a heretic. Individuals don't want to be a heretic. And it sort of forces people to basically agree on that. So whoever did that, they're genius. I mean, sort of an evil genius perhaps, but a genius nonetheless. And that's basically the problem. And people interpret data so in a way that's rational for them, but irrational for society itself. So I'll wrap up there and happy to answer questions. Thanks. Yeah, that's a really good question. So the general class of things you're talking about are these abrupt changes in the climate. And you sort of think from a chaos theory, our climate is in this one attractor, and you kind of wonder if something could happen and knock us into a complete different state. The analogy is like you're in a canoe, and you start leaning over, and at some point, you lean over a little too far, and then you flip. And people are worried about that. And clearly, if you look in the paleo record, you see things that indicate really rapid changes in climate. So, for example, about 11,000 years ago, there's a period called the Younger Dryas, where temperatures in the northern hemisphere plummeted for a few hundred years. That was the basis of the movie The Day After Tomorrow. So clearly it's happened. On the other hand, no models simulate that, and we don't, the best thing we have data on are things that happen frequently, because then you can measure these cycles. So we have good data on 11-year sunspot cycle. We have good data on El Nino. Since that's never happened before, we don't have any data on that. All we have are sort of these theories. So my perception is that most scientists believe it's possible. It would be really, really, really bad, but it's sort of unlikely in the near term. That you may have to get further away. But if we warm the temperature by a few degrees, we're in test pilot mode. We've exceeded our knowledge and our understanding. So who knows what'll happen? But it could happen. But I think it's probably unlikely. That would be my guess.
I'm a physical warming facility, so that's the
yeah.
picture. Then, as I say, it works on.
Yeah, that's in fact. There are all sorts of different models, and that's the model. Actually, I have a textbook we use in GEOS 210, which is our climate change class in the College of Geosciences, and that's exactly the model I use there. You have the atmosphere radiating up and radiating down, and you look at the energy budget of the surface. Some of it's coming from the atmosphere, and some of it's coming from the sun. And that's why, and you add more CO2, you get more downward IR from the atmosphere. That's right also. This is just different ways of thinking about.
Yeah, at least for me, that's easier to understand than your atmospheric model.
All right.
Can you comment on the possibility that some of these cognitive biases apply to climate scientists?
Yeah, that's a good question. So, what Kahan would probably say is that if you have to look at the incentives for a group. So the incentive, if you're the barber, you don't want to make waves. But you ask the question, what's the incentive for a scientist? So nobody gets ahead in science by agreeing with everybody else. If you look at who the great scientists are, they're people who overturn knowledge. I mean, my incentive is to prove I'm the smartest guy in the room, and that you do that by stomping on other people's ideas. There are lots of people out there that would love to disprove climate change. That's how you make your name. You do not make your name by writing another paper that proves the greenhouse effect exists. That gets you, a terminal postdoc. You do not want to be there. You want to prove, and so I think it's the incentive structure is really quite different. It's quite different for scientists. And there's historically there have been examples where this has happened before. So the tobacco debate, for example, and it's never the scientists who are wrong. I mean, it's always the other people that are, 40 years ago, I could be giving a talk about tobacco and how there's this argument over what is bad. And that was 20 years after scientists knew tobacco was bad. There's still this phony public debate about it. But that's a good point. I mean, you always, as a scientist, every day I think, is this bullshit? And it's just, you always have to be thinking about that. That's right. Yeah, so that's a good question. And the short answer is you don't expect even. There's something called, as I said before, the temperature, what we call the lapse rate, how fast the temperature decreases with altitude, is basically set by adiabatic motion of the parcel. You take a parcel of the surface and you start lifting it. That's really what determines it. You get some condensation of water, that affects it also, but that's what sets it. So as the surface warms, you actually expect the profile to shift a little bit. And we can see this through like ENSO cycles, El Nino cycles, where the tropics warms up. We can see how the profile changes. So, and it comports exactly with what an adiabatic parcel rising atmosphere is. And so you don't get this even shift. The upper troposphere actually warms more, and that tends to offset some of the warming. And so we call that the lapse rate feedback. It's a negative feedback that slows down. It slows down the amount of warming you get with a fixed lapse rate. Okay, so we talk about past warmings. What are you talking about, like ice ages or Eocene? I mean, is there a particular time? Because it's different. We have different mechanisms for these different periods in time. Or is there one? I'll sort of answer generally. So the general answer is people spend a lot of time doing that because obviously, if you have a car that doesn't start and every time it's the battery, the first thing you look at if your car doesn't start is the battery. And so similarly, we know the climate has varied over all time scales and it's without humans. So the first thing you look at is it natural? Could it be explained by these natural cycles? And so if you look at things like ice ages, we understand what those are to the extent that we don't have a lot of data for ice ages. We don't have good global, we have no satellites, we have no global temperatures, but we can kind of infer various temperatures. And, we understand that's caused by orbital variability on the planet. If you go back to the Eocene, 50 million years ago, the climate was much warmer. There was no ice anywhere on the planet. There were alligators living in the Arctic. And we also know carbon dioxide was much higher then. And the amount of carbon dioxide can explain the warmth. Again, you can't necessarily rule anything out because you don't have good data. In fact, we really only have good data for 30 or 40 years. And so so the answer is I think we can explain about as well as you would expect someone would be able to explain most of the variations over the planet. As you go farther back, our data gets worse and worse. So I think there's nothing in the historical record that would cause you to question that CO2 is a big control knob on our climate. So the next question you asked is, can we rule out what I'll call internal variability, which is the fact that the climate does kind of vary by itself to some extent. So El Nino, for example, is this natural oscillation of the climate. It's an internal mode of variability. And the short answer is, it's kind of like, it's very hard to rule it out because it's proving a negative. So like, let's say you're a detective and there's some suspect and he doesn't have an alibi. But on the other hand, you don't have any evidence that proves he did it. So, what do you do with that? Well, you think he probably didn't do it, even though you can't quite prove it. So for internal variability, we can't prove it's not being important, but there's no theory for it. We have a good theory for carbon dioxide. We know when you add carbon dioxide, I showed it, you warm the climate. But nobody has a theory for natural variability. There's no measurements, there's no theory, there's no evidence to support it. So what most people's views, and my view, is it's the kind of thing that you always have in the back of your mind. And if I could come up with a theory, I'd be famous. So I would certainly publish it. I'd push it. But it doesn't exist. So until someone comes up with an idea for that, it's hard to say that's right and carbon dioxide isn't, since we have such a good theory for carbon dioxide.
I thought you always shows the CO2 and the temperature tracking each other, right?
Yeah, over ice ages. That's a widely, I think, misunderstood plot, which I won't go into why. I can tell people why, but they do show that, and it is evocative.
Mistake and what are fluctuations?
Right. Yeah. So obviously, you're talking about the temperature curve. Make sure I know which plot you're talking about. You're talking about this plot. How do we know?
The temperature versus altitude or pressure.
Oh, temperature versus altitude pressure. Oh, okay, temperature versus altitude pressure. All right, so I can tell you where that plot comes from. This comes from what's called a reanalysis, which is so so this obviously it varies. It varies from place to place. This is a global average, I'm pretty sure. Yeah, it is. So it's a global average of the temperature profile. It comes from what's called a reanalysis, which means they take all the data, so all the radiosondes, all the satellite data, but the data are scattered in time. They don't measure them at the same time. They don't measure them on a fixed grid, and so they use a weather model as essentially a super interpolator. And so the weather model has all the physics in it, and so it essentially adjusts everything to give you a regularly gridded synoptic picture at 0Z on whatever date that is. Oh, it's a month. So it's probably a monthly average. But it's the average. So, you can look at the data and you can see how it varies from place to place. And this is just meant to be a schematic. There's nothing magic about this 1 month. Just to show you that it's the negative temperature grade, the fact that it cools the altitude that's important. And that when you add carbon dioxide, and you push the emission level higher, that's got to warm the climate.
So fluctuations are small?
Well, no. If you look at the tropics versus the poles, there are big differences. But for the very schematic argument, I guess I'm not sure. Do you think I guess I'm not sure what point you're trying to make. This is just sort of a cartoon to explain the physics. Clearly there are year-to-year variability. There's pole to equator latitudinal gradients.
Doing this research.
I can say. When I went to graduate school, I never thought that you'd be testifying before Congress and have people complaining to the Attorney General about you, which has happened, and the Brazos Valley District Attorney, which has happened. On the other hand, let me put it this way. I think a lot about the future. It kind of goes with the territory, and I want to make sure that nobody ever says we didn't warn them. By God, I don't know what the future holds, but I know they will not say we weren't out there telling people what the physics tells us. To be honest, there are some scientists that get it much worse than me. The guys at University of East Anglia, the Climate Gate, Phil Jones, who's really a very nice guy, he said he contemplated suicide after that. And nothing that bad has ever happened to me, but I understand how terrible it is to get in these guys' crosshairs. So I don't think I've paid much of a price. They requested my email, but they never did anything with it. There was nothing in it that they could sort of misquote and twist. I got off easy, and now I just delete all my email. So the problem has solved itself. What? Well, it's on the servers. I don't download it to my machine. It's on the servers, and the Texas Open Records law basically says that they don't have to go into backups. If somebody requests your email, I know the open records law backwards and forwards, and if they go into your email, if they request your email, all they do is look at the email, it's on the server. If it's in a backup, they do not get access to that. And that's in the law. And so, know the law. Know the law. I tell that to everybody who just going into climate, know the law, and work for a private university. That's the other thing. If you can work for a private university, you solve a lot of problems.
So maybe we can take one.
Yeah, I mean, and clearly people work on that a lot. I mean, I'm not a paleo guy, but there are lots of people working on that. And if you look at the last 10,000 years, the temperature peaked about 7,000 years ago in the mid-Holocene, and the temperature is declining until about 1800, and then it shot up. And so, we generally understand that. That's caused by orbital variations. And so we were basically heading into another ice age. In 10 or 20 or 30,000 years, if you look at the ice age cycle, we're in interglacial now. In some number of tens of thousands of years, we'd be in another ice age, and that's essentially where we were headed. But we've canceled all future ice ages, and so so clearly that's a good point. We understand it as well as I think we can. We don't have, for example, satellites measuring the solar constant. So you don't know what the solar forcing was. And so there's some things you just can't know. And so it makes it really hard to rule things out or to rule things in. But you can say that we don't see anything in the record which doesn't comport with our theory, with sort of the mainstream, what I'll call, for you guys, the standard model. There's a standard model of climate. And we don't see anything in the paleo record that disagrees with that. I can't rule it out, but until I see something which really doesn't work, you go with the best theory you have, the theory that explains basically everything.
Okay, so I think we have to cut it off here. Let's thank Dr. Dept.